Okay. Not scary at all. Yeah, well, very happy to introduce you to Fernando Rosas, who has been he's been a friend for a long time now. We met in Pio, was it 2015, 12, like that? Yeah. So you probably have seen the name. If you have not, you must have heard me mention Fernando over the last year, because he's one of the big names in basically everything that happened recently in information theory, especially multivariate information theory, emergence. There is this clique of people, Fernando, Pedro, Andrea, have been working a lot at the interface between information theory, neuroscience, and general emergence. In his actual life, he's a lecturer at Sussex, but he, as you can see there, he is like in many other places, including Imperial College and Oxford, which is actually really funny because in Oxford, if I'm not wrong, you are at the Hedonia Center, which is mostly Eudaimonia. Sorry, I get it wrong every time. Which is, basically a center focused on understanding pleasure.
No, that was the previous. This is about human flourishing.
Yeah. Human flourishing, because we cannot really use those words anymore. And no, jokes aside, Fernando has like a super. I actually forgot about this when I was reading again. Super interdisciplinary background. He had like degrees in music, philosophy, math, and then finally a PhD in engineering sciences from the Católica in Chile. And he spent a lot of time between Belgium, here of course Imperial, Sussex, and then somewhere else, which I have forgotten now. And he has been supported. This is actually a very interesting thing for me, which is supported by many different fellowships from Belgium, Marie Curie, and also something that we're going to be trying and get together, which is related to recent UK funding and international funding on AI safety, AI fusion, and so on. I'm not going to introduce your talk because the title is there, and I think you're going to do a much better job than I've done. Floor is yours.
Okay, Ronnie. Very happy to be here. And yeah, I will talk about my favorite topic, that is emergence. And I will start from sort of what I have been doing the most in the last years, that is neuroscience. And at the end, I will go towards AI safety, that is my new obsession. So, yeah, so. So to give an example of emergence, like for example, one thing that I've been very obsessed with during the last years is how do brains do their thing. And so, we have brains, and when you study brains, you can think of the structure of the brain, that means the physical wiring that connects different parts. We can think how the structure gives rise to function and activity, so you have all these time series of things happening, like nerve firing and whatever. And from there, you can extract patterns. And somehow, this combination of structure, function, and patterns generate things like cognition and consciousness, right? So then the question is, how the hell do that work? So that is a question that have interested me for very long. And of course, it's a very hard question, right? So how do we go about when we have challenges like that? And the reflex, let's take another example. Like you want to climb this mountain. What we do? So what we do normally with difficult questions is that we divide them. So the classical strategy is that first we separate a difficult question into separate parts that we can treat like one by one. Then after we have solved this separately, we connect them, and we have something like these mass production systems that you do things in a modular fashion. And we know that this works, and that's why this is our reflex on how to solve things. But the interesting thing for complexity science is that sometimes this approach fails, right? And then the question is, okay, what do we do when this fails? And part of my claim is that the difficulty to understand cognition and consciousness, like if you want to understand how the brain processes like visual information and how that encoded in the cortex, like basic sensory and motor functions, that sort of we have done a lot of progress, and the things that are more difficult are these more high cognitive functions. And my belief is that this because we try to tackle them with this type of approach, and this doesn't work. So what can we do when this doesn't work? And then we have all the cerebral complex systems that I don't need to explain here. So then you have emergence. Like, oh, maybe emergence is the thing, but what is that in the first place? And so in the presentation, I will give some ideas on how I think about emergence. This is a real photo, for example. This is the actual birds making this meta macro bird, right? And so this is sort of the thing. And my point of departure is that we have an intuition for it, right? So sometimes we see a photo like this and we say there's something special here. And the effort here is how can we formalize this and how can we put it into math? So this is another beautiful example. I got this video from Twitter when Twitter was a thing, and it's absolutely incredible. So you see how these animals, so some people say, oh, emergence is this way of talking. But this is not a way of talking. Like the way these animals work together, they have a causal influence in the world that they wouldn't have if they didn't work together, right? They can actually face this dog and keep it under control because they are being more than some of the parts. So this is the type of thing that I would like to understand. So, and the idea would be we will start from intuitions and we will try to build mathematics from these intuitions and see what we can do with this. So the menu for today, based on these initial ideas, first I will present some very high-level ideas on why does it make sense to do mathematics instead of philosophy, that is what has been the dominant thing. And then I will present, so part of my belief is that emergence is not one thing, it's multiple things, it's like a cluster of things. And to illustrate that, I will present two optional flavors of emergence, because I feel it's useful to have them side to side and to contrast them. To see, oh, they're sort of related, but sort of not the same. So I will present two types of emergence, and then I will connect things together. So before going to specifics, let's get a bit more specific about emergence. So one first useful distinction to have in mind, like this is a very simple picture, but it's useful. Like if you want to explain systems, you can be reductionist. And you can say, a duck is a machine made of parts, and they interact and they do their thing. A brain is a machine, the same as a duck. The only difference is between a brain and a duck. Well, the duck has a brain also, but the point is that the human brain is, what is special is that there are many pieces, and they're very small. That's the only difference. There is no qualitative difference, it's just quantitative. And there's a Leibniz thought experiment that if the brain would be large enough so that you could walk through it like a windmill, it would be just like a windmill, like there was no be. So according to this view, the only thing is scale. And this is a position that I think is perfectly reasonable. Another position is to say, well, even if we manage to get the perfect particle theory, so we solve all the particles, we will still not be able to predict stuff like communism. And I think most people will agree, except some people in some physics departments, but most people will agree that that prediction is not possible. So the question is why that is not possible? And then there are basically two types of explanations. One is to say that is not possible because it's just not possible. Like it's in principle impossible. And then you are in the realm of something that sometimes is described as strong emergence. And the idea here is that there are some macro properties, some big things that have causal power that cannot be explained in terms of the causal power of the parts. And this is a position that some people take. Another, a bit more parsimonious explanation is to say, well, the impossibility exists, it's real, but it's only in practice. It's a matter of that the prediction can be done in theory, but it's just too hard. It will require too much compute, too long, would be a thing. So in practice cannot be done, but in theory it could be. And then the idea is that the causal power is always reducible, but sometimes very impractical, and then we don't do it because, things. So I feel these three positions is useful to have them in mind. So if you ask the question, is it possible to a big thing to have causal power that is not reducible? These three positions will have these different answers. Reductionist would say no, just no. Strong emergence would say yes, of course, in some cases. And then the debate would be what are those cases? Maybe human consciousness, maybe economics, whatever. Then the weak emergence would say it looked like, but it actually not. And of course, there are much more, and the real philosophical debate is much deeper than this, but it's sort of a good, to delineate the space of options, these three positions. Now, what is my personal, a bit ironic take on this, is that it's a bit of a pillow fight because first, there is no definition of what is a causal power. And causality is this thing that until you start thinking about it, it seems simple. And the more you think about it, it's like a rabbit hole, and then you get completely confused. Like causality is a very complicated thing, and you cannot start discussing the question if you don't have causality. Then what is to reduce? We also have discussed that. Also, from a bit of a physics background, would it be nice to have a minimal model of emergence, where we could reason about something concrete instead of arguing the hands like this? And could we measure something also? That would be nice. So, taking all this, my position, personal position here, is that I see two extremes here. One is to say emergence is this magical thing that as soon as you explain it, it's not emergent. That's a bit of a dead end. It's not very productive, so I don't like that. In the other extreme is like emergence is just nothing to see, please keep walking. That I also don't find very useful because there is something special in those systems. So my interest is to explore the space in between. Like what type of positions you can take between these two extremes that I don't find very helpful, and from a mathematical perspective, like what are the actions that you have to put in, and what are the theorems that you can cash out of those assumptions. So more concretely, my interest is to build a lightweight framework to reason about emergence in a way that you can formally specify what you mean, because I don't think saying, oh, this is emergent is enough. You have to be like, okay, but by that I mean this. And by being able to formally specify what you mean, the hope is that you can measure something, and then you can evaluate this empirically. Because also my interest is, could we do empirical science with this? Like, could you measure the brain and do some measurements in brain data and conclude stuff empirically instead of like, convincing you out of my hands that they move so nice, right? so that's sort of my hope. And there is an interesting question about the philosophy of emergence and the math of emergence. So the philosophy of emergence has been very long in the work for many, many years, and the math of emergence are much more recent. And I think math is not coming here to replace philosophy and to take over. It's a complementary thing. So what math can offer here is that math is very useful to lead reasoning in complicated places. Like for example, if we start thinking about infinite dimensional vector space, and we go crazy, but math helps. Or you start thinking, this infinity is larger than this infinity. Intuition breaks, right? And emergence also intuition breaks a bit. So I feel that math is very helpful to guide intuition in those places. The second is that math is very nice to have very concrete, specific definitions that then can be translated into things you can measure. So I think that's my way of thinking what can contribute. And there's also an interesting question about philosophy is asking like, what is the nature of emergence? And in a way, we're bypassing a bit that question by saying, okay, how can we operationalize it and use it? But I think if you do that in the right way, that if you try something and it works or it doesn't work, then you understand more what it is. So there is potentially a virtuous circle between these two things. And so I don't think these are competing, and I hope they can be good friends. So that's, I switched the section, I forgot that, don't worry. So with that's the intro, and now I will present these two alternative views on emergence. I will present first, I usually do the other order, but I decided to switch last night and I didn't change it. So I will present first this whole minus part view of emergence based on information decomposition and synergy and all of that. And then I will go to this hierarchical view that is a bit different. So I will start with this. So in this view of emergence, we are going to focus on system made of parts. So for example, a flock of birds is made of birds, and a group of humans is made of humans. So like we have these single parts that move together and they have this collective. And the informal definition of emergence will be when the whole has properties that can be traced down to that's the initial intuition. Now to formalize this, I take inspiration in this classic paper from '94 from neuroscience, where the intuition, these three people, they were thinking about what's special about the brain as a physical system in contrast with other physical systems. And the intuition was, well, the brain is special because every part of the brain is doing something different. It is differentiated, like the visual cortex is different from the frontal cortex. They have different functions, but it's integrated. So they have this interesting balance between doing their own thing, but doing it together. Now, that suggests some sort of trade-off, right? And some sort of optimal trade-off. But I think my reading of this paper is a bit different. Is saying under some conditions, you can actually have these two things at the same time. Which sounds weird, because how can you be integrated and differentiated without trade-off? But a geometrical example, what I have in mind is this. This is the Borman ring. It's a geometric construction where if you, with your imagination, you take the blue ring out, the red and the green will not be connected. and if you take the red out, the green and the blue. So this is a triple construction that you cannot separate them, but it only happens when you have the three things. As soon as you take one out, the thing disappears. So this is a geometric triple interaction that cannot be explained as a connection of pairs. And this is in this sense, I believe the systems are differentiated but integrated. So as a whole, they are connected, but as subset, they can do whatever they want. And this is the way I think of synergy and how I think synergy is sort of having the cake and eat it, or at the same time, in a way. And I think this is special about the brain. So how can we operationalize this idea of synergy? And here, this is a cartoon story to explain how we think about synergy in terms of information theory. So the idea here, this is sort of a cartoon story. Like, let's say I'm in my house, I have my favorite cookies, and I wake up in the morning, I want my cookies, I go to the kitchen, they're gone. So I'm very angry, so as a rational human being, I will hire a detective to find which of my flatmates ate my cookies. There are 9 cookies. So this detective is going to have 2 witnesses to get information from. And the first witness say, well, I saw the cookie was wearing a mustache. And by learning that, you are ruling out more than half the witnesses of the culprit. So good, you're learning. And now it was wearing a hat. So, and with that information from the first witness, you almost got the cookie. Now it goes to the second witness and say, yeah, mustache, and it was a red hair. And by knowing that, you rule out a different set, and by combining both, you know who the culprit was, right? So the interesting part of the story is that you realize that these types of informations are qualitatively different. Mustache was given by both, so it's redundant. It's information that the detective could have got from the first or the second witness. Hat and red hair is unique. It was given by one, but not by the other. But the identity of the culprit was actually given by both and was not given by neither. And in that sense, we say there is the synergistic information, there is the extra bit that you can conclude by having the 2 sources at the same time. And this is sort of the whole more than sum of the parts type of thing. So this is the intuition, and the beautiful thing is that you can do some mathematics that I will not bother you with, that if you take the information theory and you do some simple stuff, you can operationalize this and compute it, and there are lattices and there are all sorts of stories. But it can be measured, and it can be measured from data. So the idea is that we took this idea of synergy to try to operationalize emergence. And how does this work? The intuition here is that we have a multi-parted system. So the state of the system at time t is a vector and has a dynamic, so it evolves in time. And we have a coarse graining of the system. So for example, if you have a flock of birds, maybe V is the center of mass. And then you can check the dynamics of the flock as the dynamics of the center of mass. Right? And now you have the system described at 2 levels of resolution, either as birds or as the center of mass moving around. And the question is how these 2 scales interact. And intuitively, we're going to argue for 2 types of emergence here. One is causal decoupling, that is when the center of mass know where it's going, but the birds don't know. And down causation would be something like the center of mass is affecting where birds are going in a way that other birds are not affected. So I like thinking about inflation, for example. Like inflation goes up, so my salary disappears, but I cannot blame any individual human. It is a collective thing that's pushing me in ways. Well, sometimes we can blame. Now, more mathematically, the definition that we say about emergence, we say, okay, we have a system X, we have a candidate quantity for emergence V, and we say V is emergent from X if and only if V is providing unique information about the future of the system, conditional on the past of the future. So, and there's a trick in this definition. So you're saying V is providing information about the future that is not provided by the micro. And you could argue, of course, this doesn't make sense because this is a coarse grain of this. So you have less information here from here. So how could you provide unique information from less information, right? And the trick is that the unique information, this is sort of encapsulated in the notation. You're conditioning not with respect to the vector, but with respect to the parts separately. So it's like you ask, bird number 1, where is this flock going? I don't know. Bird number 2, you know? No. But maybe both together they could have told. But you're not allowing it. So it's like first order information, you're conditioning on first order information and allowing second or any other order information. to be part of this unique stuff. There is a generalization, you can say, or emergent of order K, where you are conditioning up toward the groups of size K, and I will talk more about it. But for the presentation, to make things simple, it's just about the individuals. So basically, you're considering all the information in the individuals, you are conditioning on that, and you're saying if B says something beyond the individuals, it says something. That's sort of the basic intuition. Now, to give you a toy model, this is artificial, but it's useful for thinking. We have two binary things. We initialize them randomly, 50-50, 50-50, so they start both being white. And now the rule is the following. If they are equal, they're going to stay equal with very high probability. But if they're equally white or equally black, it doesn't matter, completely random. So they start by chance being equal and they stay being equal for a long time. At some point they shift, they keep being different, and at some point they shift back to be equal. But from here to here was just by chance that they stay the same or they flip. And what is interesting about this system is that if you are the first person and I'm white, I cannot predict anything. Like, you cannot say anything about what will happen, like absolutely nothing. And the other person will be in the same situation. So this is a society made of two people that they say this world is completely wicked. Like, I can't predict anything, this is all random. But there is something going on, right? It is not chaos. There is this, we call it a statistical ghost. The parity is a ghost floating on society and preserving itself, right? And it's quite interesting that the mathematics allow this to happen. This is like, oh, weird, but the statistics make this happen. And this is the type of thing we have in mind when capturing emergence in this way. So these collective effects that can perpetuate themselves in a way that the parts could be ignorant, completely ignorant. Does that make sense? Good. So this is the basic framework. Now, this is a definition so far. We have three main theoretical results out of this single definition. The first is to say, if you remember, the definition is for a specific V. So I have a candidate V, I want to test it. Now you could ask, is there something intrinsic in X that allow for such a V to exist? Is there anything in the dynamics that allow emergence to happen? And the answer is yes, and the answer is synergy. So there exists something emergent if and only if the dynamics are synergies. We are not defining emergence as synergy, it's a consequence of the definition as this unique information. All right? So, and this is telling you, if you want to see just the dynamics, the emergence is sort of the capacity of the system to have emergence. Is that right? The synergy is the capacity for emergence. This is the first result. Now, this is why this is useful is because then you can do some black magic, and you can take the synergy and do some tricks and split it in two parts. And these two parts, there are some other theorems that say this is related to downward causation and this is related to causal decoupling. Causal decoupling is the case of the parity we saw before, that's the coupling. So the parity affects the parity and it's not affecting anyone below. If the parity will be determining, okay, you first person will be equal to the parity, that will be downward causation. A collective property is affecting the future of a specific part. But the beauty is that these two modes of emergence come naturally from the mathematics. So it's not that I was one day in the house and say, oh, it'd be nice to have two modes. It's more like the math is suggesting it in different ways. Now, so far, this is a beautiful theory, mathematical theory that is not very applicable. Because for measuring things, you would need to estimate joint probabilities of many parts and it would be a pain. So theorem 3 is what makes this practical. And this is a sufficient but not necessary condition that if this is satisfied, emergence is there. If it fails, it's inconclusive. So it's in the good direction. And the idea here, let's say you have the flock, bird flock, and we have the center of mass as a candidate for synergy, for emergence. We are measuring here sort of the autocorrelation of the center of mass, so how much the center of mass knows where it's going. And let's say you can predict 30% of the future. And then you predict the center of mass from each of the birds. And you sum that up together. So the question is, from the prediction of the single birds, do I explain how much the thing predicted itself or not? And if the center of mass predicts itself more than what every bird predicts, and then you sum it up, then there is something interesting going on. So that's intuition why this works. But this is not necessary, because here, this part here, maybe bird number 1 and bird number 2 can predict with the same information. So you're double counting. And that's why it's sort of over conservative to do that summation. But we do it because all of these are pairwise statistics. So if you have two numbers, you're doing pairwise statistics and you compute this. So it's super scalable. The only problem with this is that the more parts you have, the more double counting you will have. So if you have the game of life with 1 trillion cells, it might fail. But you can still measure it, and if you're lucky and it works, it works. and we have some studies with the game of life that it did work. So this is nice because this is what makes the theory practical. And there's all sorts of tricks to make it a bit more precise, that we are working in different ways, but this is the basic version. Now, to give you an example, this is what I was saying before. So these are some models of bird flocks. There is a parameter about avoidance. So in this, everything is very rigid, so the birds stay, and the center of mass, the red, is just staying there. In the other extreme, the birds ignore each other, and it's a complete mess, and the center of mass also is a complete mess. And the center is sub-balanced. And the intuition is, in the crazy bird's case, the center of mass don't predict itself, nothing predicts itself, so they not, right? So that doesn't work. In the military bird case, every bird, so the center of mass predicts itself, but every bird predicts the center of mass also, so it doesn't work. But in the middle, there is this interesting regime where if you ask the different birds where the red dot is going, they don't know, but the red dot knows to some degree. So it can predict better itself than what every bird that composes that center of mass knows. And in that sense, there is emergence there. Is it clear? So this is the simplest, more intuitive example from all of the one we have. So that's why I presented. We have a number of more results in different papers. And then you can compute this quantity and do statistics and all of that. And you can see that for all values in between these two extremes, there is clear emergence, and in the two extremes, it's so this is this version of emergence. Now we have a number of studies on brains on this. I took 2, and also in artificial neural networks. I took 2 from biology. Here we have data, fMRI data from people with brain injuries. So we have 10 subjects in vegetative condition, 11 in minimally conscious, so they are sort of a little bit conscious, but not really. So they have the injury, but not so severe. And then you have the same number of controls to contrast. And what we did was to compute this capacity for emergence. The problem here with fMRI is that what is the center of mass of the brain? So if you know the V, then you can apply the whole thing and it's great. But it's not very easy sometimes to have a candidate. So in this case, we didn't have a candidate, and because of that, we compute the capacity for emergence, but then you cannot use the tricks to dimensionality reduction, so you cannot do it all over the whole brain. So we did it on pairs of regions. So this is basically, we computed the capacity for emergence in every pair of brain regions. And we did that for the 3 groups, and this is what you get. So there is more capacity for emergence in controls than in minimally conscious than in vegetative state. So the capacity for emergence drops with less consciousness. So there is a lot of technical limitations. This is sort of a first step because there's a lot of things we would like to do better, but it's encouraging first result. And there's more to say, but this is sort of one example of application of this theory. There's another example we did that we computed. So in here, basically, the red thing is the capacity for causal decoupling, and the blue is this other thing that I haven't spoken so much, that is about redundancy. That is the opposite from the synergy and emergence. And if you plot these 2 things across the brain, you get this if you know about neuroanatomy, this is strikingly clear that sensory motor is very redundant, very non-emergent. And the front and the back in something called the default mode network is very synergistic, very emergent. So this is a very long paper with a lot of results. I'm putting a few. So there is first this division. then here we did the same trick, that because we didn't know what to look for, we computed these capacity terms. And because we did it for every pair of brain regions, we end up with a network. With a network of synergy and a network of redundancy. So then you can compute the network properties of these two networks. And we see that the synergy network is very non-modular or efficient, and the redundancy network is very modular and very non-efficient. So they are very different as networks. And the other interesting bit is that we took the wiring, the physical wiring of the brain, and if you do the similarity with the redundancy network, is much more similar than for the synergy network. So the synergy network, that is the cause of the coupling thing, seemed to be less constrained by the physical substrate. Another interesting finding was that we did the same calculations on the monkeys, and we found that the level of redundancy is similar, but the level of synergy is completely different. And the intuition here is that it seems that redundancy is more sensory motor, and it's reasonable to think that monkeys engage in the same type of sensory motor activities we do. But the synergy part is about self-reflection and planning and blah, blah, that's completely different. So this is supporting of that intuition. And then another result, and there are a lot more in the paper, but this is another one. This is cortical expansion, meaning how much different brain regions expanded between monkeys and humans. And this is the synergy to redundancy gradient, and there is a correlation. So more synergistic areas expanded more. And this is the degree to which different brain regions express genes that are distinctive of humans and with respect to monkeys. And again, positive correlation between synergy and expression of these special genes. So in summary, the take home from this part is that these two types of information seem to have different functions. So redundancy seems to be relatively input-output, robustness, things are quick, they cannot fail, a trigger is coming, I have to jump by it, Synergy is more this crazy thing that if it fails, it's fine, but if it works, it's great. So like doing poetry or math or something. And which is more related with frontal and the development network and this very human distinctive features. So yeah, that's one type of emergence. I will do a recap at the end, but the intuition here is these parts that are more than, the whole that is more than some parts. Now, let me present a very different view on emergence. I'm going to surprise you well with that. And this is going to be not about parts anymore, but about scales, like levels of resolution. So, and let me warm up the story. First, there is a story about nature that seems that nature is naturally structured in this way. Like we have all these, scales that in biology, in physics, there are different scales, and then in society, etc. And then it seems that our knowledge, our scientific disciplines are structured also in a way like that mirrors nature, right? So we see this multi-level structure everywhere. Now, another interesting question is, this seems to be a different question, but I actually I'm not sure how different it is. What are abstractions? Like if we have a bronze sphere and this human thinking about it, and it's like, oh, this is spheric and it's also made of bronze. Is this related with scales and, and in a way it could, because you could say, oh, I make this distinction or I don't make it. So I don't care about the shape and I only care about what it's made. So you could think of that as a coarse grain too. So is this related with the other? I think it does, and maybe it will convince you, maybe not. Another related question is the brain a computer? And also, again, when Twitter was a thing, every 2 or 3 months there was this fight, very angry fight about the brain is obviously a computer, obviously not. And people got very angry. And my take on the problem was that I was getting people very worked out about this, but under some definitions, the brain was obviously a computer, and the other definition was obviously not a computer. In neither case, I was learning much. So I started thinking, can I think of what a computer is in a different way that is not Turing machines and all that, such that I can learn something about the brain? And from that point, with colleagues, we start thinking about, okay, what to make a laptop different from other physical systems? Because a laptop is a physical system, right? That is following Schrödinger's equation. and as everything else. So what does it make a computer? And the thought was the following. If you have a laptop and you open your Python and you write that code and you execute it once, you will see a 5 in your screen, right? If you execute it again, you will see a 5 again, but the physics that lead to that output are going to be completely different from the first time, right? Every time you run the script, the physics are changing, but the software level remains stable. So it seems that there is a decoupling of scales. You have one level that's completely crazy, it's almost like turbulence and whatever, and unpredictable, uncontrollable. But you have this other scale that where you program, and you could take that scale, you could implement it in a different physics, but you have again the same logic. So it feels that that separation of scales is what makes a computer. So, and starting from this intuition was like, okay, if we take this as a definition of software or computer, can we check if other physical systems behave like this? Which other physical systems behave like this? And we identify this when we are not sure about it, because the computer obviously works. And so there we took a similar starting point as before. So we have a physical system evolving in time. We have a coarse-graining function to go to the macro level. And then the question was, what type of macro level interaction should we require in order to say there is software? And let me convince you that the toilet is running software. So the idea here, this is my favorite example of weird places where you start seeing software, when you start thinking like this. When you flush the toilet, there's some water and you flush the toilet, the water goes out. There is a floating device that goes up. And now the water starts flowing in. And as the water goes up, it eventually will push the floating device up. And then that will shut off the entry of the water and the stuff. Now, my claim is that this is instantiated in very complicated, Navier-Stokes dynamics, but at the macro level, there is a while loop. Like while this thing is down, keep floating, and the thing is up, then you shut it up. So there is a logic, a macroscopic logic here, that don't care about fluid dynamics, but is instantiated in fluid dynamics. It's supervening on that thing. And in that sense, I really think there's a Python script running here, in a way. So this is one example. Another example, let's take a self-driving car. Self-driving car, you have this Tesla, and it's moving forward. Self-driving cars have relatively very limited sensors to move around. They have this camera, there may be infrared, whatever, but they don't measure, quarks or electrons or anything. All reality is made of those, but they move around based on very coarse-grained observations, and they do it just fine. The same way that we do that, right? We are made of quarks or strings in 11 dimensions, but we don't see them, and we do fine. So I think it's sort of the same thing happening here. Now, how can we formalize this? Our first idea is information closure. So we have these two scales, we have a coarse-graining mapping. So information closure is when you do a prediction about the future of the macro. So I want to know what is the level of the toilet in the future or something like that. And in one case, you do it based on macro information. So you have the macro history, and you do the best prediction you can about the future. And then alternatively, you try to predict the same thing, but based on micro information. So in principle, this should be larger than this. You should be able to do a better job at predicting because the micro has more information than the macro. And this is idealized, so there's no overfitting, no misestimation or anything. So in principle, this is larger than this, but maybe for some coarse graining, these are equal. What would that mean? It means that the macro has all the information needed to predict itself. There is nothing, if let's say the macro information is for free, and the micro information you have to pay. You have to go somewhere and rent a microscope to see the micro. And this is telling you, under some conditions, you shouldn't pay that money because it will not give you useful data. It will give you more data, but it's not useful for the task of predicting the macro. So information closure means macro levels that are self-sufficient in terms of prediction. This is the first definition. And for people that are familiar with transfer entropy, this can be framed as a transfer entropy of no information going from micro to macro. Another question was about causality. So one is about prediction. The other causality, like, can I control the thing, and sort of the intuition here would be, I try to control my system, steer it to get specific macro outcomes, and I do either a macro steering, so I have fat fingers, so I can only control big things, or I have very thin fingers, so I can set my condition very precisely. Could I get better macro, more controlled macro outcomes by micro fingers, or is macro fingers enough? And how can we formalize this? And at this point, we got into something called computational mechanics. Have anyone heard about computational mechanics? No? So the idea of computational mechanics is, in a nutshell, you have some data, the data is X, and you coarse grain, so you consider histories of stuff, and for different histories, you consider what are the predictions that they give about the future. So here you have two different histories, but somehow they have the same conditional probabilities for future events. So the idea here is if two different histories have the same forecast, informationally they are good. Like you would not want to keep that distinction if your job is about prediction. Instead, this and this, these are different histories, but they have different predictions. So you should make that distinction. To give an example, like if you have data that is Markovian and you didn't know, you start checking which histories give different predictions, and you will realize that every history that shared the same last guy, independently of what was before, is the same prediction. So in that case, the only distinction you keep is what it was the last value. That's what Markov is. If the system is not Markov, if it is Markov over the k, you will end up keeping the last k. It can be Markov infinite, super non-Markov, then you keep more complicated stuff. But the idea of an epsilon machine is keep the distinction that make a difference. And starting from this intuition, what we came about with this idea that just for fun we call it the upsilon machine instead of the epsilon machine, so here you have two scales, macro and micro. There are two epsilon machines that you can build in terms of distinctions that make a difference for the same level. So here are distinctions, this is E sub t, these are distinctions of the micro that make a difference for the micro. You have E prime, that is distinctions of the macro that makes a difference for the macro. But there is also a construction that is on diagonal, so there is distinctions in the micro that makes a difference for the macro. And in principle, this is a coarse graining from this, because you're controlling less stuff. Like there are less things that you care about predicting. So if there are less distinctions that you would like to keep in mind. So there is a relationship between these three things. And causal closure, the way we define it here, is saying a macro process is causally closed if U is equal to E prime. And the intuition here is if all the distinctions from the micro that could make a difference for the future of the micro are actually distinctions at the macro. So there is no distinction that you would like to make in order to steer a different future that you couldn't make already at the macro. Does that make sense? It's a bit more complicated, but it's about keeping distinctions and coarse grainings. Like, it's also related with sufficient statistics. If people are familiar with that. So you are building sufficient statistics of the past with respect to the future, and basically every distinction that you could want to make, you are making it already in there.
And the coarse grains don't have to be constant in time, right? As in
no, can be different. In the paper, I didn't know enough about statistical mechanics, but yeah, they can be non-stationary.
And they can also, let's say, encompass like longer or shorter amount of time. So for example, at some point on your epsilon prime t, you have a collection of them, I assume, because you have a set of trajectories. Like there could be some that have a certain amount of memory, and others like different.
Yeah, so the way to define this is the equivalent classes of infinite trajectories.
Yeah.
But in practice, it could be distinctions that are more or less complicated. So for me, the more beautiful thing of computational mechanics, that what we saw about causality is nice, but this is the real thing that I find more interesting, is the fact that on the one hand, you can see an epsilon machine as a HMM type of description. So basically you have data and you're constructing the minimal Markov process that happen in the hidden space that are these distinctions that explain the data in a simple graphical model. But you can also think of this as a finite state machine, if you're familiar with finite state machines. So finite state machine means I'm in a state And now this is sort of a funny thought experiment. Here, the state generates the observation. Here, the observation is coming from my pocket. It's like, oh, I want this to happen. And from here, by what you put, you are transitioning to another state. And you are moving between states based on inputs that you're putting for your pocket. But this type of dynamic that you are moving around because of the different inputs, that's sort of a notion of computation in some way. In computer science, usually you build finite state machines to recognize formal languages or all sort of things. So this dual representation, this more dynamical and more computational, I find it very inspiring. So I was thinking, how can we cash out this view in a multi-scale way? And what we came up with is a question of, could you have an epsilon machine that is these small circles with arrows, and could it be a way that you coarse-grain states and you also coarse-grain inputs such that you get sort of a nested machine, a simpler machine? So here you have a lot of states and you're directing it with this very fine alphabet. And here you say, okay, forget about it. I just want to track like simple things, and I move around with a more coarse alphabet. And the idea here is that if the definition, no, I forgot to put the formal definition, but computational closure is when the epsilon machine of the macro is nested on the epsilon machine of the micro. And maybe I thought that this was always the case, but this is a rare case. Like the reason is you can have a micro that is Markovian, so the epsilon machine is simple, but when you coarse grain, you can make a non-Markovian thing. So sometimes the epsilon machine of the macro can be more complicated than the epsilon machine of the micro. But here you're requiring to be not only more simple, but also nested in the other. And let me illustrate that idea with an example. Here we have a network, a modular network, so strongly connected within and weakly connected between. We put a random walk on this. So I guess you're quite familiar with this type of thing. So random walk on this modular network. And now we're going to describe it at 3 levels of resolution. First, we're going to say at where initial condition random, and then you let it run. First, you describe this time series in terms of exactly in which node this drunk person is. Second level is you say in which community it is, but you have no idea where within the community. And the third level is the size of the community, not even which community. And you can prove that this thing is computationally closed, informationally closed, and constantly closed. Computationally closed means that you could run the whole dynamic at the level of communities, and the simulation would be perfect. Like, I'm not making an approximation if I want to simulate this in a Markovian way here. It's just a perfect simulation. Or you could simulate this as a random shift between this, and you're not approximating anything. Like, if you run the whole thing and then you do statistics here, it's the same thing as running the appropriate Markovian process at this level. And so, and what I like of this is that let's say this is a computational process of deciding where you're going. By doing this, you are sort of factoring the computations at 3 levels of resolution, and you can decide how much resolution you want in your computations to keep track of. So the beauty of this approach is that one computation that can be very daunting, because there are many states that are possible and may transition, you're sort of dividing it at levels of resolutions, and you could tweak that upward depending on what you need at different moments. So this is a notion of computational approach. Now, the big story here is that let's say you have some data, you can do statistics, and then you can coarse grain and do coarse grain statistics and do it again. Then you could build the epsilon machines at every level, and these are going to be some explanation of your data in terms of finite state transitions of some hidden macro process. And if computational closure happens, there is a diagram that commutes. And the idea here is that, let's say this is vertical arrows are coarse grains, and horizontal arrows are going from data to theory. In the sense that you could say the epsilon machine is like the theory that explains my data. And the commuting of the diagram means if I take the theory of my data and then I coarse grain the theory, I get to the same point that I would get if I coarse grain my data and then I build the theory of my coarse grain data. And then emergence would mean that thing in this case. Do you follow me? And this is sort of reminiscent of, how classical mechanics is a coarse-grained version of quantum mechanics. So you could have a quantum experiment and you get a lot of data, and then you explain it at the level of quantum, and then you can coarse-grain it and get a classical explanation, or you have quantum data, but now you coarse-grain it, and you have classical data, and then you do a classical explanation, and the whole thing arrives to the same. And that's sort of the intuition. And when this works, then the successive state machines are coarse-grained of each other, and they're nested in this nice way, which is not normally the case. But usually, the epsilon machines at different levels are completely a disaster, and they don't like each other. So this is sort of the big picture idea. So let's say this is a conceptual picture. Let's say you have a system that can take 5 values. So you have time series over 5 possible values. You are very not smart, so you try all the coarse grains. And these are all the coarse grains. So this is a coarse grain where everything is like 0, like you're killing everything. Here you are coarse graining 2 things, 3 things, 4 things, and 5. So these are all the scales of your system. Now, from all the coarse graining, you keep the good ones, the informationally close ones, the ones that are self-contained in terms of information. This is good because now you can, like, intuitively, the shape of this lattice is informative on the scales of your system, right? It's telling you all the scales that are self-contained. The idea here is that you can even go further, and you can now do a lattice not of coarse graining, but of epsilon machines. And what is interesting is that sometimes you have different coarse grainings that map to the same epsilon machine. So usually this coarse graining is simpler than this. To give a simple example, let's say you have some big data, you coarse grain it in a way that you get IID noise. So that is not a constant, right? It's noise. But when you do the epsilon machine of that is actually this epsilon machine. It is a state that goes to itself because there is no computation. So there are different things at the level of data that at the level of computation they will look the same. And then having this type of lattice, in my view, gives you the anatomy of the computations in a more clean way. So this is sort of the idea. Now let me give you some toy examples. One, have you heard of the Ehrenfest diffusion model? So this is a classical statistical mechanics world where you have 2 chambers connected by a thin tube, and there are particles here or there, and they can switch between them. And the 2 levels would be either which particle is where, so 0 or 1 if you are here or here, and how many particles are here, how many particles are here. And you can prove that this is all computationally, informationally, and causally closed. Meaning that if you want to keep track of the number of particles in one side, this is a Markov process, and you can represent it in an epsilon machine that looks like this, and you could do if what you care is the mean values, you can simulate this and forget about the micro. So this is a super simple example. An example, an epsilon more exciting. I guess you have heard of Hopfield networks, have been in the news. So the idea intuitively, Hopfield network, you have these patterns, the network learns these 5 patterns, and then you initialize the system in some random place, and it's going to end up usually going to the place that is the closest. So what you can show is that if you define the dot product between every possible the memorized pattern and the actual configuration, now we're representing this in terms of these 5 numbers. And you can show that this is also computational equal. So basically, if you want to know where the thing is going to end, you could keep track just of these dot products. You don't need to check the whole thing because how the Hopfield network works. So this is another super toy model that is saying the computations in this type of Hopfield network doesn't really happen at the level of neurons, because there's a lot of symmetry. Like if I switch 2 things such that I'm equally far away from 2, the probability of going to here stays the same. And with this, you're sort of isolating and explaining the dynamics at a much simpler scale. We're working on less, more complicated and interesting examples with real brains and transformers, but they're in the making. So maybe in a couple of months, I can tell you more about that. So I'm about to finish. So as a summary, this type of emergence tells us about scales that are causally autonomous, And there are two ways to think why these are interesting. For the system itself, it enabled this a couple levels that are easily controllable. And I think for us as thermodynamic beings, that's crucial. Like we couldn't live at the thermodynamic level. We can't control that, but we have these levels of macro levels that are very controllable. And for a researcher, if you have a system and you identify all these scales, you could run your simulations at the level that you want. Especially if you're doing agent-based modeling, maybe you're burning a lot of joules for no reason. And you could run your simulations at this coarse-grained level, and you're going to get perfect predictions. You're not sacrificing anything because you are identifying these good decoupling scales. Now, as a very brief example, to tell you a little bit what this is all work until last year. In this year, I have been getting obsessed with AI safety, and I'm applying these ideas in the context of AI safety. So, you all have heard of AI agents that are coming, and they're great, but they're also a bit, I don't know if you have seen this movie. Great power comes with great responsibility. So AI agents are going to be great, but there are a lot of sources of risk. It would be nice to have ways to evaluate that they are safe. And one idea is to test AI agents in sandboxes. So basically, you have an AI agent, and instead of deploying it to the world and see what happens, you are going to create a simulator that is going to give the agent, for the agent is going to be indistinguishable for reality, and in the simulator you can do whatever you want. You can run it, you can test all sorts of things in the environment. So the idea is that you are given an AI agent, you have no idea how it works, but if you have a world model to sandbox it, then you can do all sorts of things. Now, imagine that you can do that. Well, it could be, maybe there is a way to build this model, but maybe it's too expensive. Like, let's say you have a robot and you do a simulation of the whole planet at the level of quantum mechanics. That would be great, but forget about running it. So maybe your model is too detailed. Maybe it includes things that the agent would never interact, or is too resolved. Maybe it's quantum and the robot is classical. So it would be nice to know two things, basically. One is, what is the minimal world that you need in order to run the world in a way that is realistic? And the other is that, could we learn something about the agent by finding that minimal world model? And so the thought experiment that I took as inspiration was this idea of the brain and the bat. So the idea here is that the story goes, if you have a brain and you put some electrodes such that you stimulate the sensory areas in the right way, and you're reading from the motor areas such that you simulate a perfect feedback, like sensory feedback loop, then the brain will not be able to tell that this is a simulation. It will think, oh, I'm in this field running and something. So, and based on this story, the idea was, can we put the AI in a bat? So AI in a bat. What is important from here is that you don't put so much emphasis on the world model, but more on the interface of the agent with the world. It's more about how the agent can act, what do the agent perceive, and how do you mimic that sensory motor loop instead of simulating the whole world. So originally usually you're going to be given this, so the agent has some actions, affect the world, they have a state, and based on the state you generate some observation. And the question is, how can you compress this world such that this part remains the same? So we put in the archive a paper last week that I will not go into details because I'm running out of time, but as an overall idea, there are different routes. We found a fundamental trade-off between compression and interpretability. But long story short, the most compressed world model has negative probabilities, which is a bit weird, but it works. So maximal compression is very uninterpretable, and there are other ways to do compression such that you get Bayesian beliefs, and then that gives an upper bound on what an agent could learn. So there are world models that tell you what an agent could learn. There are others that are just computationally efficient, and we map all these options and provide algorithms and all sort of things. And so that's what I did until last week. And what I'm doing now, and you understand because of what I have explained, is now, what about lossy compression? Because the other is the best you can do lossless. But why, if that is still completely intractable? So now, what if we compress a little bit the actions on the sensory, such that we can further compress the world? And the idea here is that computational closure will be installed. Like, can we identify what are the scales of the world that are decoupled so that we can do a perfect simulation at that given scale. The same machinery from before, but now applied to a sensory motor loop instead of a whole world. And so then you have to extend the notion of information closure, the same as before, and then expand the definition of computational closure, and you can do the whole story. So, and yeah, so that's what I'm working at the moment, and if you're curious, let me know and I'll do more. So with that, let me start wrapping up. So, what is emergence? Did we learn something about it? Well, my take on this is that emergence is a bit like intelligence or complexity. So it's
Nice
not
word.
it's not one thing, but it makes sense to speak of it as is the one thing. Like it's useful to speak about intelligence, but as soon as you become serious about intelligence, you have to be more specific. Right? It's the same with complexity. Like with your friends in the pub, it's fine to speak about complexity, but when you write a paper, you say, by the way, by complexity I mean this. And I believe the same with emergence. So it's a cluster of properties that tend to go together, but they can be disentangled if you try. And my view of the field is that we are now, before we were fighting what is the right measure, it's the same with complexity. Right? What is fights of what is the right measure of complexity? I don't think anyone fights about it anymore. And I think with emergence, we are transitioning to that point where there's no any more fights about the right measure of emergence, but more about, okay, how all these frameworks relate to each other? And are they the same, are they not the same? If you think about the causal decoupling and the information closure, they're sort of similar, right? But they're actually not similar. And you start thinking about it and breaks your head a bit, but that's progress. So the next step is to really understand how these things fit and to what degree they are different or not. I present these two flavors of emergence. One is emergence as computational closure, meaning the coupling and relative autonomy between scales, and emergence as whole more than the parts, where synergy. And you can see that they are sort of similar, but also similar. Again, I'm not saying these are the only flavors. I have worked on these flavors and I understand them, that's why I present them, but I think there are many more. And the task we have in front of us is now to start mapping the space and the geography of this space. Don't forget about this is another talk. And finally, what is emerging the answer for this? We don't know, and because all of this is very new and there's a lot of work to be done, so hopefully we can all collaborate. And with that, I think done. Yes, so thanks for my girlfriends in this work, and thank you for your attention.
Questions? There was something online?
Yeah.
Kind of a technical question, but when we're looking at synergy, say we have two stochastic processes, right? And we're thinking, well, we have one stochastic process, and we're thinking about the synergy. Is there an assumption there that the noise grows linearly with scale? Because could you have a situation where if the sort of criteria is that mutual information at the higher level is greater than the mutual information of the sum of all of its parts?
Mm-hmm.
Can you have a situation where you have a non-linearly growing noise, which sort of is going to fall into that mutual information, and that leads to this sort of greater than relationship, or does the fact that it's mutual information is already non-linear, does that take care of it?
I think if the noise is IID between time, it's not going to contribute to any mutual info.
But if it's if it's IID.
If you have correlated noise in time, then it could be complicated. But then why is that noise?
Yeah, right. But it's not noise, right? Okay. But it doesn't matter if it's noise, if it's sort of the combination of all the noises is greater than the sum of those.
Yeah, as long as the noise has nothing in common between T and T prime, then the thing will not affect these calculations.
Okay, cool. Emergent noise.
Yeah, exactly.
Yeah.
So something I struggle a bit to understand in the part of the computational closure. So it's like, if we say that there are these different levels, and it's like we are trying to say if they can be decoupled or not, and there's also something about the emergence or whatever. But so how are we sure that, for example, if we are looking at the micro, to compare it to another level, which is macro, we need to take a measurement of the micro, and this will take assumptions of the micro, or will discard information that already will be part of the micro, and then we are kind of like measuring something that is related to the other level, and how like do we make sure that this is not also like a way that we are like forcing or not forcing a couple or a couple on these levels. I don't know if it makes sense or not.
Let me try to answer to see if I understood. So one important caveat is that the here, for example, so whenever you make a statement, usually you have some macro level with respect to the micro, but the micro is a bit arbitrary because the micro is always a macro of something else, right?
Yeah.
And maybe something is not emergent with respect to something that was below. So in that sense, all the statements are relative.
Okay.
And the statements are as good as your micro in some sense.
Okay.
Right? So in defining the micro, you are making a commitment, and all your conclusions are going to be related with that.
Okay.
I don't know if that answers the question.
So you're always okay. No, okay, yes.
Another point that is related with that is also important, is that, let me go to here. So, for example, this example is very not rotational invariant. Like if I re-encode this system and I have one part is the party and another is something else, then it's not emergent. So in this case, emergent is with respect to this specific way of presenting your system.
Yeah.
So for example, if you have a flock of birds, it makes sense to have a vector where every component is a bird. If you have a Lorentz attractor, you have 3 components, but you have no attachment to any of them. So I would not use this framework to analyze that, because you don't have attachment to that specific thing. Or maybe you want to do it, but then you want to do rotation to see the thing is robust to rotation. But in that sense, there has been a bit of a hassle, but it's interesting that these 2 frameworks, the second framework is about scales and is transformation invariant. And this one is not. But I don't take that as a bug, more as a feature.
Okay.
Like here, you're embracing a factorization of your system, and it will tell you something about that factorization, and it's useful as long as you care about that factorization.
Okay.
It's funny how an emergent notion of emergence depending on the factorization that they have, right?
Yeah.
Anything else? Yeah. How much of these? So when you're looking at you're showing about all the whole lattice of partitions, how do you filter that? How much does this look like fitting a hidden Markov model in practice or something like that?
So are you asking how tractable it is to do a brute force of the course?
Actually, I'm asking how you do it. Do you do brute force, or do you have guidelines to do it, and how do you scale it? Because, for example,
Yeah, I mean, the short answer is that we don't do it. Because we are building right now, this is a theoretical framework that we don't have the computational tools to actually do it at scale. For that, the way I see it as, well, actually the thing that we're doing is that you can forget about the factorizations in data space because you have to try them all. You compute the epsilon machine of the micro, and then you look for something called you find the factorizations of the micro that gives Markov processes. This is something called likability, and not like most coarse grainings of Markov don't give you Markov, so you only check the ones that give you Markov, and there is a good chunk of literature method for that. So yeah, so that's one thing that's one of the directions we're trying. The other thing also about how estimating epsilon machines and all that. There is one of the things I'm working at the moment a lot is about if you have data and you try to feed a perfect epsilon machine, maybe you will end up with 1 trillion states because you didn't have enough data and you get some weird thing in your data. So it makes sense to have not a perfect fit where you have an epsilon error that you can play with. And there is something called rate distortion and function bottlenecks that sort of is very well suited to this. There is one paper on fitting epsilon machines and rate distortion. There is another paper I didn't mention that maybe I should. That is, they found epsilon machines and transformers. So the claim is transformers are computing epsilon. So my hope is that then we can twist the thing up and say, in the beginning, you can do, so one very attractive use of epsilon machines is that they tell you a ground truth of what to look for. So if you have a system that is learning something, like it's doing a prediction task, you can prove that the epsilon machine is a minimal structure that allows perfect prediction. So if the system is good, you could try to look if it has an epsilon machine inside. And people have found it. So if now you strongly believe that the transformers are estimating epsilon machines, now you can use transformers to estimate epsilon machines. And there's a whole literature on computing information bottleneck with neural networks. I think that's the future. So I'm going that direction now, like looking what are and it feels that there's something very like, you know, the two things are very connected. So, and it's also very nice to have this distortion measure where you can trade complexity, how many states you keep, and how much error you make, and also for the story about word modeling. So I'm waiting for the reviews of this paper on the AI in Nevada, but one thing that people are going to tell me is that this is completely impossible to do, right? This story. So they're going to tell me, like, the optimally compressed system is going to be a computer because it's too large. And I would say yes. But the question then is like, okay, how much I can further push this if I allow small distortions and then the distortion theory. And another part of this, that I think you will appreciate, is that I think to scale this, I need two things. One is the distortion, and another is to say the world is actually not a blob. It's made of chairs and coffee mugs and trees. So if I know that the world is made of pieces, how can I exploit that into the compression? And one thing that I'm tracking that I find very exciting, the potential, is that this is not a total order, which is interesting. Like usually when we think about scales, it's usually a totally ordered set. But here you have this branching. So maybe if you take anti-chains like this can be maybe a factorization. Like maybe you get a tree here and another tree here. So that type of thing I also find very promising. And in my organization plan in my mind, you will have a combination of great distortion over parts of the world. And then you factorize all these things separately and then you can scale it.
Yeah, I know this will sound completely idiot because I'm not an expert, obviously, but this reminds me a lot. In theory of computation, you have like this equivalent and minimization of state machines. And all this process, isn't it what it's doing more or less?
That's a very good question. So here, bisimulation is that. So there is a whole literature in computer science where you have a machine and you have a behavior. There's a whole story about mechanism and behaviors there. And so you have a behavior that is the formal language that is being recognized by the machine. And then in the deterministic case, there's a standard procedure that is called the Meidner road that you can find the minimal automata that recognize that language. There is and then the natural question is to say, oh, epsilon machines are like that? And they are sort of like that, but not exactly. So what happens is that in the probabilistic setting, the thing is more complicated because you have, there's a whole section about the paper focused on this. So if you want to minimize the world and you have no constraints on what the world looks like, you don't have an epsilon machine. You can compress more, but generally the world is not predictive. So the agent couldn't compute the world in real time.
So it's more like a non-deterministic state machine.
They're all going to be stochastic automata, but the problem is the epsilon machine. The interesting property is that if you're an agent and you're getting sample by sample, you can compute the thing because it's a equivalent class of things that you have seen. So you can compute it in real time. But if you do the minimization in brute force, you will get something that cannot be done like that. So now if you say, okay, I don't want to minimize any world, I want to minimize all the worlds that are computable for the agent, then you get the epsilon machine. So the epsilon machine is the minimal world that can be computed in real time. And in that sense, we say that that's this route. So it is the route for interpretability because that tells you the epsilon machine is the thing that a very smart agent should do. And everything that is in the epsilon machine is what can be learned, and everything that is not in the epsilon machine is an hallucination. because it's something that was not learned from the data, it's something that the machine thinks, but it does crap. So I think the absolute machine gives you like an upper bound of what is learnable from the data.
Thank you.
There is one question in the chat that was asked at the end of the part one about redundancy and synergy. Ryan asked, how might you study the ability of emergent capacity to predict collective intelligence, say of the collaboration among a group of scientists toward making a discovery?
That's a great question, and not so much, and it's something I would love to do more. There are two sort of related questions there. One is that to what degree synergy allows the system to do more things that it could do normally. I suspect that one paper we have that is very beautiful is that, let me remember, so you have artificial neural network and it's learning two tasks, and the tasks can be similar or different. So if the tasks are very similar, you can learn them in sequence or like this, and then you can learn them both because they're not so, there's no catastrophic forgetting or anything, and then you get learnability, but you don't get synergy. And the only way that the artificial neural network shows synergy is that if you manage to learn two tasks that are very different in an interleaved way, because if you concatenate two tasks that are very different, you learn the second and forget the first. But so in that sense, we have some indications that there is something about flexibility and synergy, in the sense that if you have enough neurons, you could learn half of the neurons learn the first task, half of the neurons learn the second task. There's no synergy and there's good performance. But if you don't have enough resources to separate the things, and you want to learn the same thing with both, then synergy appears. Now, so there we have some indication that that is true, and it's sort of intuitively true, but there is not enough work to have a conclusive answer. The other thing that I would love to learn more is that what we have done so far is usually a way to detect synergy when it happens. But you could ask the other question, like, how can I promote synergy? Like, what type of mechanism generates synergy? And that is something that we know much less. If you say, oh, I have this company, and I think synergy is cool, so I would like to generate synergy in my company. Like, what should I do? I don't know. So that's another direction that it would be interesting to know more.
Okay, I think that was good. So let's thank our speaker again.
You want to stop the recording?